So in this class, we are going to be looking at the nature of matter. Remember that from the introduction of chemistry, we defined chemistry as the science that deals with the study of matter, its properties, its structure, and the changes or transformation that matter undergoes, right? So in our previous class, we did do the definition of matter. We defined matter, states of matter, properties of those states of matter. Now we want to look at the changes, the transformation that matter undergoes. All right. So it is categorized into two. The changes matter undergo are of two types. You have physical, right? Physical change. A matter can undergo a physical change or a chemical change. These are the two types of changes. These are the two types of changes. So we are going to differentiate between these two transformations and what is their significance when it comes to chemistry. Okay, so let's start with the physical change. Physical change in matter is easily reversible. Don't forget that, please. A physical change is easily reversible, and it does not form any new substance. No new substance is formed, which means the content or chemical composition of whatever substance is undergoing that change remains the same. Okay, it does not change. For example, water, when you heat water, it becomes steam, right? It's still the same H2O, whether it is liquid or in the gaseous form, the same H2O. That is a physical change. It can be reversed. Steam can be converted back to water through the process of condensation, right? Now, but in a chemical change, there is a challenge with reversing that change. So it is not easily reversible. In some cases, it is permanently irreversible, right? Not easily reversible. Not easily reversible. And the reason is because a new substance or new substances, a new substance is formed. A new substance is formed. So we are going to still look into these things in more details, all right? So just keep this in mind that we have two kinds of changes that matter can undergo, the physical change and the chemical change, all right? So let's look at examples now in explaining these changes and how we can easily identify them. Let's see examples of physical change. Number one, you have boiling of water is a physical change. I've mentioned that example. Boiling of water is a physical change. Okay, because the content of water is H2O, right? The content of water is H2O. That is the chemical composition. Now, whether it is in the liquid state, okay, the one that we call water, all right, or in the solid state, ice. When you freeze water, you know it becomes ice, right? That is the solid state of water. Or in the gaseous state, what we call steam. Okay, they have the same chemical composition, water. Nothing has changed. No new substance has been formed. So it's a physical change and it can easily be reversed. For example, liquid water can be converted to ice by freezing, right? By freezing. Liquid water can be converted to solid water, ice, by freezing. Liquid water can be converted to gaseous water, steam, by heating. Through the process, we call that process evaporation. Is that not so? Even this gaseous water, steam can be converted back to liquid water by a process called condensation. Is that not so? Okay, we'll still get to that. There, another example of physical change is removal of stains. Removal of stains using solvents like petrol or kerosene. Okay, so removal of stains is a physical change. There is no new substance that is formed. The stain remains what it is, and the petrol or kerosene, which is the solvent, remain what it is, not affected, not altered. Okay, so then let's go to examples of chemical change now. Examples of chemical change. Okay, remember that the chemical change is not easily reversible, right? For example, number one, rusting, or I can say corrosion. Corrosion is the general name. When a metal is exposed to air in the presence of water and it changes form, you call it corrosion. When it happens to iron, you call it rusting. Is that not so? Rusting is a process in which a pure iron is converted to iron 3 oxide in the presence of air and water. So this is the cause of rusting. All right, there must be air and there must be water for rusting to take place. It's a chemical change actually, because this is the original state of the iron and now it has become this, which is different from this. This is a new substance, so it's a chemical change. You cannot easily reverse what you have now back to its original form. Okay, so all you can do is to prevent rusting. Once rusting has taken place, it is difficult to reverse. Then number two, let's even say digestion of food. Digestion of food, the enzymatic digestion of food, right? When you take in carbohydrate, your starch, for instance, from rice or another food substances, you are going to have glucose as the end product. So once food has digested to its end product or its final form, you cannot reverse it. It's irreversible. It's irreversible. Then another example is burning. Burning, all right? For example, when you set fire on wood, for instance, you set fire on wood, it burns to ashes, right? You can't reverse that process. You can't reverse that process. But in chemistry, there is a definite burning alone does not mean when you set fire on something, all right? In chemistry, there is a way we define burning. I want to explain it so that next time you hear me say burning, you know what I'm saying. Burning is a reaction between a substance and oxygen. Please put that in mind. It's a reaction between a substance and oxygen. So if I say a substance undergoes burning, what I'm saying is that substance reacts with oxygen. Please don't forget that. Okay, burning is a reaction between a substance and oxygen. Okay, these are examples of chemical change. Okay, now burning can take place in many forms. You can have combustion, burning of magnesium reborn. That is when magnesium reacts with oxygen. Combustion, mainly carbon, when carbon reacts with oxygen, all those things. Okay, so but for now, let's just keep it cool like this. I believe you are following me, right? So I've just said that we have examples of physical change, we have examples of chemical change. For example, boiling of water is a physical change. Freezing is a physical change, all right? Condensation is a physical change. Melting is a physical change. Do you get that? It's a physical change because something you melt can also solidify to give you the same thing again. So it's a physical change. Then examples of chemical change, you have rusting, in which iron is converted to iron 3 oxide, or metal. A metal, when exposed to air and water, changes form. All right, it's difficult to reverse because a new substance will be produced. So it's a chemical change. Digestion of food to its final form is difficult to reverse, right? Then burning, when a substance reacts with oxygen, it produces a new substance. For example, when carbon reacts with oxygen, I can have either carbon 4 oxide or carbon 2 oxide. Carbon 4 oxide that people call carbon dioxide, right? But in chemistry, you call it by its IUPAC. due to the oxidation state, carbon 4 oxide, carbon 2 oxide. Now, it can be carbon 2 oxide if the oxygen is limited, if it is insufficient, all right, is limited in supply. It will be carbon 4 oxide if you have excess oxygen reacting with carbon. We'll still get to that when it comes to reactions in chemistry. Okay, so there are terms that I want you to be familiar with. As we move on, I want you to be familiar with what melting is. Melting is a process in which a solid becomes a liquid or turns to a liquid, or a solid is converted to a liquid by the action of heat, all right? By the action of heat, okay? When a solid turns to a liquid by the action of heat, that is melting. Yeah, another one is, you can call it solidification. Solidification is the opposite of melting, right? For example, when you heat candle, it melts into wax. But if you allow it to cool, it solidifies again to give you candle, right? So solidification, in solidification, liquid becomes solid again, right? Okay. Then you have let me mention sublimation. Sublimation is the conversion of solid to gas when you heat that solid without melting, without passing through the liquid phase, and the liquid phase would have been melting, right? Without passing through the liquid phase, which means there are certain solid substances that if you heat them, they will not melt, they rather turn directly to gases. For example, examples of such substances are, you have iodine crystal. When you heat iodine crystals, you are going to have iodine gas. You see, another one is ammonium chloride. So these substances, they do not melt to give you the liquid form, rather they turn directly to gases. The opposite of this sublimation is what I call, or what science calls, deposition. When a gas becomes solid without passing through the liquid phase, all right? Without passing through the liquid phase. You see that? So for example, iodine gas can still undergo deposition to give you iodine solid crystals. Do you get that? Okay. So you call such substances that when you heat them, solid substances, they become gases without passing through the liquid state, are said to sublime. These are examples, okay? Then you have what is called condensation. Condensation, this one, of course, we know it mainly deals with water. When steam or gaseous water becomes liquid, all right, that is condensation. When steam or gaseous water becomes liquid, you call that process condensation, okay? Then you have evaporation. Evaporation, when liquid water becomes gaseous or steam by the action of heat, right? By the action of heat. Okay. Then you have liquefaction. Liquefaction, please take note of these terms. Liquefaction is when a gas or gases are made to become liquid. When gases are made to become liquid, for instance, although they do not lose their gaseous nature, a simple example is the cooking gas that we use at home, right? You know, if you shake that cylinder, please don't shake it, all right? But you discover that it's as if it's liquid that is inside. but it's not a liquid inside, it's a gas. That's why when you open that control, when you turn it on, you can perceive the gas coming out. So, and it does not look like liquid, whereas inside the container it looks like liquid. It's because the gas has been liquefied. Okay, the gas has been liquefied. So when the gas takes the form of a liquid, okay, another one is the gas that is inside a lighter, gas light. So if you see the gas inside, it looks like liquid, but if you break it open, it's volatile, it disappears. It becomes gas immediately. So it has been pressurized to look like liquid, but it's not exactly liquid. Okay, so that is that. I hope you are understanding me. I've just explained some terms that I want you to be very familiar with: melting, solidification, sublimation, deposition, condensation, evaporation, and liquefaction. Okay, so I want to tell us the differences now in a tabular form, the differences between physical and chemical changes. So difference between physical and chemical changes. Then the first one, a physical change is easily reversible, right? Easily reversible. But a chemical change is not easily reversible, and it may not be reversible at all. Not easily reversible. Then you can have no new substance. No new substance is formed. Okay, H2O is H2O, whether it is in the liquid, solid, or gaseous state. Then here, a new substance or new substances, a new substance is formed. All right, a new substance is formed. Then here you don't have change in mass. The water that you freeze to have ice is still the same in mass as the liquid water. So there is no change in mass. No change. There is no change in mass, but here there is change in mass. Change in mass. Then you can have heat may not be involved. Heat may not be involved. Heat may not be involved. But here you always have involvement of heat or liberation of heat. Heat is involved. Okay, so see these as simple differences between a physical and chemical change. Okay, they are very important. Please take note. So a physical change can be reversed easily by a physical means, right? You don't need to add any chemical, unlike the chemical change. All right, so let's move on now. Let's move on to elements. In the last class, you discovered that I introduced some elements and then I mentioned something about the periodic table. So I want us to look at it in more details here. Okay, I want us to look at this in more details. I defined it in the last class as I defined periodic table, right, as a system of arrangement or classification of elements according to their atomic number. Okay, arrangement of elements according to their atomic number. Don't forget, it's atomic number, according to their atomic numbers. According to their atomic numbers, not masses. Okay, not masses, according to their atomic numbers. So, but today we are going to limit ourselves to just the first 20 elements, okay, for your level. The first 20 elements. So I'm going to list those elements. Before I even define element, I want you to know the examples and how they are arranged in the periodic table. Okay, now we can, after that, because my intention is to explain the implication of this arrangement in the periodic table, is very important to your knowledge of chemistry. Very important, very important. So I'm going to deal with the first 20 elements here. We are going to list them and we are going to arrange them in the periodic table, and I'm going to explain what is the implication of that arrangement in the periodic table. How does it give certain properties to the elements? Okay, so let's look at the first 20 elements. Let's look at the first 20 elements. First 20 elements. Number one, you have hydrogen. So you have hydrogen is the first element in the periodic table, and the chemical symbol is H. Okay. Number two, you have helium, and the chemical symbol is He. Lithium, and the chemical symbol is Li. Number four, beryllium, and the chemical symbol is Be. Number five, boron, the chemical symbol is B. Carbon, the chemical symbol is C. Nitrogen, the chemical symbol is N. Oxygen, the chemical symbol is O. Fluorine, the chemical symbol is F. Here you have the first 20 elements. Alright. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, this is neon, Ne. Sodium, Na, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Please take note of their chemical symbols, because in chemistry, when you want to write organic compounds, or when you want to write the chemical formulas of compounds, when you want to write chemical reactions, you use symbols. Okay, so knowing these symbols are very, very important. So when I say sodium chloride, don't start thinking of the spellings first. Let the symbol come to your mind: sodium, chlorine, sulfur, carbon. So these symbols are very, very important of the periodic table for the first 20 elements, although we've not filled in the elements, which we are going to do together. So you can see that a periodic table has 8 groups. Normally, a periodic table has 8 groups and 7 periods. Okay, but in this case now, since we are just dealing with the first 20 elements, we will limit ourselves to 4 periods. Okay, so now we are going to put those elements in their respective places in this periodic table. So the first element, remember, the first element is hydrogen. The second element is helium. Okay, there's a reason why there is this gap between hydrogen and helium. You will still learn that. Okay, now then the third element is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. These are the first 20 elements in the periodic table. Very easy to arrange. So these elements here, all of them are called group 1 elements because they are under group 1, right? This is group 1, group 2, group 3, and like that. So these are group 1 elements. So if I ask you to mention group 1 elements now, you can mention hydrogen, you can mention lithium, you can mention sodium, you can mention potassium. So these ones are group 2 elements: beryllium, magnesium, calcium. These are group 3 elements: boron, aluminium. These are group 4 elements: carbon, silicon. These are group 5 elements: nitrogen, phosphorus. Group 6 elements: oxygen, sulfur. Group 7 elements: fluorine and chlorine. Then group 0 elements: helium, neon, argon. Okay, group 0. You do not call them group 8 because there is a reason for that, which, if time permits me, I will explain. Now, these elements in their respective groups have corresponding number of valence electrons. You know, when we say valence electrons in chemistry, we are just saying the outermost electrons in the shell, or the electrons in the outermost shell of an atom. Okay, for example, hydrogen. Hydrogen is in group 1 because it has only one electron in its shell, which is also the outermost shell, because hydrogen has only one shell. Okay, so let me explain it this way. All these elements that are in group 1 now, all these elements that are in group 1, they have valence electron of 1, which means they have only one electron in their outermost shell. I will explain what shell means, okay, with time. Just know that the valence electrons of all group 1 elements is 1. The valence electrons of all group 2 elements is 2. The valence electrons of all group 3 elements, 3. Group 4 elements will have valence electron of 4. Group 5, they will have 5 valence electrons. Group 6 will have 6 valence electrons. Group 7 will have 7 valence electrons. Group 0 will either have 2 or 8 electrons in their outermost shell. Okay, helium has only 2 electrons in its outermost shell, which is complete. Neon and argon have 8 in their outermost shell, also complete. Okay, so you call these 2 duplet configuration, and then this 8, this one's having 8, they have octet configuration. Okay, no, octet means 8, oct, right? Okay, duplet 2. So what is now the implication for this? What's the significance of this period 1? When I say an element is in period 1, what do I mean by that? It means that element has only one shell. That is, hydrogen has only one shell, helium has only one shell. The elements that are in period 2 have 2 shells: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. They have 2 shells. The elements that are in group 3, they have 3 shells. All right, in period 3 rather. The elements that are in period 3 have 3 shells. The elements that are in period 4 have 4 shells. Okay, first 20 actually in the periodic table. With time you move on to the first 30, and then on and on. You will learn a lot now. But if you see a normal periodic table, right, you discover that it's not like this. This one is just for the first 20 elements. Is that not so? So you discover that there is a gap between period 2 and period 3 in the normal periodic table. That is where you have elements called transition elements. Elements like iron, titanium, vanadium, zinc, copper. All those elements are called transition elements. They are found between group 2 and group 3 elements. Okay, that is element from number 21 to 30. They are transition elements. Those are the first transition elements. Okay, but for now, you are limited to just these first 20 elements for now. So, but if you still want to know the first 30, so element 21 is, okay, let me just write it here. Element 21 is scandium. How do I put it now for you to see very well? Element 21 is scandium. 22 is titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. This is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, this is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, that's 21 to 30. These are the first 20 elements, and here you have 21 to 30. Okay, so if I say in these first 20 elements now, if I say you should mention the element that is in group 2 period 3, element in group 2 period 3, first of all you come to group 2. These are the group 2 elements. These are the group 2 elements, right? So, but I'm looking for the element that is in group 2 period 3. So if this is group 2 and this is period 3, so let me trace them. Group 2, period 3, the point of meeting, the point of intersection, that is at magnesium. So it means magnesium is the element that is in group 2, period 3, right? So what of element in group 4, period 2? So I'll come to group 4. This element is in group 4 and is also in period 2. This is it. This is period 2 and this is group 4. So this is the element. If I say group 4, period 3, this is group 4, period 3. Do you see that? Okay. So please remember that the elements in a particular group have corresponding valence electrons. For example, elements in group 1 have valence electrons of a valence electron of 1, actually just 1, a valence electron of 1. Elements in group 2 have a valence electrons of 2, just like that, 3, 4, 5, 6, 7. But when you get here, the reason why they are under this group 0 and not 8, all right, is because they have complete electron configuration. Okay, they are called noble gases or rare gases or inert gases, which means they are not reactive. Why? Because they are complete. The reason for chemical reaction or chemical combination is because of instability. So the atom wants to be stable. So all the atoms from here to group 7, they are unstable on their own. So they have to combine with others to achieve a stable state. But these ones, they are already complete. They are stable. So they don't need to participate. That is why you will never see them participate in any reaction. You will never see a noble gas in any reaction, in any chemical reaction, because they have complete electron configuration. They don't need to give out and they don't need to receive. So they are on their own. Okay? All right. So we'll stop here for today. In our next class, we'll be dealing more with elements now. We'll be classifying them, where you have metals like alkali metals, alkali earth metals, where you have metalloids, non-metals, and how you can identify them in this periodic table. Thank you. Enjoy your day.